Welcome everybody to today's video. Today we're going to talk about data and particularly signage and being able to move data from a smaller register to a larger and vice versa. It's relatively easy to make something smaller. So we can convert, for example, we can convert a word to a byte and we just simply remove the upper 8 bits. And we'll go through an example here in doing that. When we move the data around, we just lose some of the values. We just lose some of those bits. And so you can see here that we're going to move this value 1, 2, 3, 4 in hex. This h here, this lowercase h, indicates that that's a number, a numeric value represented in hexadecimal. We can move that into AX, and that's 16 bits. And then we can take in this next instruction and take the lower 8 bits and move that into CL. And that's relatively easy to do because what we'll end up doing then is we'll simply end up taking these bits and moving them into CL. Right? As a refresher, we have our registers. And again, we're a 32-bit world, and so we have a 32-bit register. So if this is EAX, then this is the full register is 32 bits. We can cut that register in half, and we can have, or we can directly reference AX, and that would give us 16 bits. And we can also cut that one in half, and that would give us AH and AL. Both of those being 8 bits. So we can reference those portions directly of any of our registers, or most of our registers anyway. We have this upper 16 bits here that we can't necessarily reference directly, although we'll talk about some shifting operations that indirectly allows us to do that. So what we want to look at then with this particular example is if we move data into AX and then we move the lower bits into CL, so lower 8 of AL into the lower 8 of CL, what ultimately is in CL. Right? So if we look at our register, and let's say that we have our lower 16 and we have 1, 2, 3, 4 in hex, and then we move that lower 8 bits, 3, 4 into CL, then what we should have in CL is 3, 4 hex. Okay, and we can take a look. We can do an example here. All right, so I've got a program. I did gen.sh to generate the project, and then I just called this video 11 to hopefully match up with the videos as I'm numbering the videos. These are the files that I'm working on. So gen.sh to generate that video, and then that gives us a project folder with our assembly file. And once we run the script to build our executable, we'll have that as well. So oftentimes what I do in order to just make it a little bit easier is on the command line, I'll run the script to assemble and link and then generate the executable. I'll use 2 ampersands, and then I'll also execute the executable itself. So this will build the program and then run it as long as this one finishes successfully. If we generate a syntax error or something, then this will fail, which will cause this to fail. And then sometimes I even just put a clear in there as well, just to make it a little bit easier. All right, so that's what I'm doing there. As far as the program then, what we'll do is we'll start off, I want to just review a couple things first before we get into the actual movement of data there. And so let's just dump regs and run this program and see what happens. All right, so there we go, we've got our registers, and we can see that in pretty much all of the registers there is some value. You know, all of these registers that we could potentially use in our program has some sort of a value. And so oftentimes what you'll need to do, because we don't know what these values come from, we don't know where they came from, we don't know what their purpose is, and as far as we're concerned, they don't mean anything. And so oftentimes what we'll have to do is we'll have to zero out a register. We'll want to zero it out to make sure that none of this previous data causes us any issues. And so the easiest way to do that is to execute a move. So we say move into EAX the value of 0. Right? Remember, this is the source and this is the destination. So if we make that modification and run our program, you'll see that we've now zeroed out EAX. Okay, that worked. We can move a single 0 value into EAX because we're referencing the entire register, EAX, then that zeroes out the entire register. If we didn't, let's say that we do BX, so we move 0 into BX, then what would happen is something like this. right? We'd have a 0, we'd essentially zero out those lower 16 bits, but the upper 16 would be left untouched. And so we would still have potentially junk in there. Sometimes you don't. Sometimes, like this particular register, at the time that our instructions were executed, there was no value set. And so it all depends. That's not necessarily going to be consistent. That's going to be dependent upon what's going on in that operating system at the time that you run your program. Another way you can do it is also to do XOR. And so our XOR command is one of the bitwise operators, and what it does is it exclusive ORs. And so if you exclusive OR something against itself, you'll never have an exclusive situation. You'll never have a bit, because you're looking for that exclusive test to come back to be true. You need to have the two bits that you're comparing. One needs to be 1, one needs to be 0. But because you're comparing the same bits to each other, they're always going to be the same. And so you're never going to get a 1. And so this is, and here we can see when we run it, this is another way to zero out that register, which is what we see here. You'll see this a lot with shellcode. We'll talk about shellcode here in the next couple weeks, and that this helps prevent putting a null byte into the shellcode. And oftentimes with shellcode, we're taking advantage of a program's string handling functions, an overflow of some sort typically. And the way that string handling works, especially in a C program, is it looks for the null byte. And if we send shellcode that includes a null byte, then it might abruptly end our shellcode, so it might not actually work. So we'll go through that in a little bit later, just because that tends to be a little bit more of a security topic, but just so you get some exposure to it here. All right, so I'll leave that there. I'll go ahead and zero out a couple other registers because we're going to use them. Goodness, if I can do it correctly here. Okay. So the first thing that we'll do then is we'll move into EAX the value 1, 2, 3, 4 hex. Okay, and then we'll dump our registers. So we can see, after we run that we have the value 1, 2, 3, 4 hex in the lower 16 bits of that register. The upper 16 bits are zeroed, and they would be zeroed because regardless, because I used all of EAX here. So because I used EAX, we didn't necessarily need to do this XOR here. And we can prove that by commenting out that XOR and running our program again. We'll see the upper 16 bits are still set to 0. Now, if I make that move, but let's say that we only move data into AX. So now we're only moving this value here into the lower 16 bits. We can run our program and we can see that those upper 16 bits are going to be set to something that we don't know. We don't know what that value is. Right? And so then if we later on use the full register EAX, that could cause us issues, because this value is certainly not the value 1, 2, 3, 4 in hex. Okay, so I'll make sure to leave that zero out instruction there. And now what we'll do from here is we'll move into CL the value of AL, and we'll dump our registers. So let's see what we get there. All right, so here we have, right, the lower 8 bits, and we move that value here into the lower 8 bits of CL. Okay, we could also, let's say that we wanted to move into BH the value from AH. It was a little quick there. There we go. All right, so there's those 8 bits right there, and we moved them into there. Right, and so we can move data around anytime that we want using any of those portions of the registers that we can directly access: EAX, AX, AL, AH. You'll notice that when we move the data, right? So when we moved from a larger register to a smaller, what happened? We just lost the leading zeros, the leading bits, not zeros. I'm sorry, the leading bits. They just disappeared. They just got truncated, and so we just moved it. So it's relatively straightforward. It's relatively easy to do that. What about when we have a negative value? What if it is signed? We need to keep the sign, and that's where it becomes a problem. So let's say that we're working with the value -7. right? We know that when we look at 2's complement and storing a number in 2's complement, that we have the most significant bit. Back to my pen here. The most significant bit, if it's a 1, then that equals a negative value. If it's a 0, then that equals a positive value. And so depending on the number, if we were storing a value in 2's complement, and this was the number that was being stored, this is our most significant bit, this is our least significant bit. And so we would look at this value. If it's set to 1, then we know that this number is negative. If it was set to 0, then we would know it was positive. All right, so -7, how would we store that in 2's complement? Well, if you did the conversion, you'd find that it's F9. And at this point, you should be able to do that. You should be able to take that value, -7, and convert it into 2's complement to see how it would be stored in hex or in those bits. And so what we'll do then is we'll take a look at that, and we'll move that into to BL. And what you'll see is if we look at that in binary, of course, we'll have all 1s, and then 9 should be 1001, which is our F9. Now let's say, because that's a smaller register, right? We can store that number in that byte, right? That lower 8 bits is a byte, and that's the smallest amount of memory that we can reference. So even though we could represent -7, well, we need a byte to do that. So now let's say that we want to move that into EAX. So we want to go from a byte, into something much larger, which is EAX. So go from that 8 bits to 32 bits. We have two options. That's our sign extend instruction or 0 extend. And what we have with these instructions then is, so we're moving from that lower register, right, which is, let's say, this is our value here, and this is AL or BL, I guess in this case, right? If we all of a sudden we have these additional bits available in this register, what do we do with those bits? What do we set those values to? Well, a sign extend, what the sign extend is going to do is it's going to look at that value, it's going to look at the most significant bit, and then it's going to extend that bit. Okay, so if we look at this value, the most significant bit is a 1, it's going to extend that value. So that way when we fill up that larger register, we fill it up with the appropriate sign, because now we have a full 32 bits, and so this becomes the most significant bit, and we need to make sure that that has the same, it's set the same as our original value. If this happened to be a 0, we would still, if we're telling it even with the sign extend, if this happened to be a 0, then it would fill this with zeros. The most significant bit would be set to 0, right? But it looks at this value and it extends that value into whatever register we're moving into. With 0 extend, what the 0 extend does is it extends zeros regardless. So it doesn't look at the most significant bit being set in order to determine how to extend. It just simply extends using zeros to extend into that register. Okay, so here's an example of sign extend, very similar to what we were just talking about there. Let's say that we move the value -7 into BL, and now we want to sign extend BL into EAX. And so what we're going to find is that we're going to fill F's all the way up in that register, because F, if we look at F in binary, that's 1, 1, 1, 1. We're going to extend 1s from that original 8-bit register all the way through those 32 bits. So we'll take a look at an example here. Just a second here. For whatever reason, the timeout's been really sensitive on the server tonight, so All right, so there we go. All right, let's zero out EAX again just to make sure it's very clear what we're doing. Okay, so -7, as we saw, F9, and we can see in the register, AL, that we have the value F9. And so now we want to extend that. So let's say that we want to move the value of AL into EAX. Well, we can say move sign extend into EAX AL. Or no, let's do EBX just so we can look at two different registers. Okay, and there's the result. So we can see that it looked at that most significant bit. It would happen to be a 1 here, and now it sign extended that all the way. And so now in this register, we have 1s extended all the way, so we have all 1s, or we have Fs as far as the values set in the register. Okay, let's say that let's zero out the registers again, and let's move into AL value of 7. And then from there, we'll move sign extend into EBX, the value at AL. And then we'll dump the registers. Right, and there we can see the result. So we move 7 into AL, we can see that there, and then we sign extended that value, that register AL, into EBX. And because the most significant bit set was 0, then we got all zeros here. Okay, the other instruction then in what we have to deal with or use when we're moving data around is the zero extend. And so we can see a very similar example as we've done previously here, but instead of sign extending, we'll zero extend. So this time, let's move into EAX a value of FFFFFFH. Okay, and we'll dump the regs just so you can see what that looks like. Nope, too many. There we go. I had to put a 0 in front of that because we'll talk about variables and labels and stuff. This 0 means to not treat this like a label. Don't treat it like a variable. The assembler will get confused there. So whenever we use something that's alphabetic as far as a value, and when we run into that when we use hexadecimal values, we have to put a 0 in front of that. Okay, so that moves into EAX all 1s, or all Fs. And so from there, let's say that we move into AL the value of -7. Okay, and we can run the program again. You can see there we have F9, but we still have a bunch of zeros. And now let's say that we move zero extend the value of AL into EAX. Right, and there you can see EAX, we extended zeros, it ignored the most significant bit, and now the value of this register, if we were going to print off the value of this register, and we can do that, you can see that it's not -7. So we dump the registers. We can use print int, and print int will print out the value of whatever's in EAX, and then we'll also call print new line. Right, so 249, which is not the same value that we had before. Right, because we started with -7. But because we zero extended, we lost our sign bit. So let's see. I guess just to prove, we could move into EAX -7 and then call that again. So print int and call print new line. And there we see it printed off -7. All right. Okay, and so there's an example very similar to what we just went through, and as far as zero extending. So again, we're just looking at so zero extend ignores the most significant bit. It just simply extends by zeros. Sign extend looks at the most significant bit and then moves according to whatever that bit is. If it's 1, it extends 1. If it's 0, it extends 0. And so what this really boils down to then is that when you're moving data from a smaller register to a larger, and you care about the signage, then you need to do sign extend. If you don't care, then you can use 0 extend. So that's all I have for this video, just talking about those two instructions. The next video then we'll talk about arithmetic and look at multiplication and division. Let me know if you have any questions. Thanks.